Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So thank you very much for having me here. When I was first contacted and invited, I had a little back and forth arguing with the people who invited me that they perhaps had the wrong person or the wrong conference, because I've never even been a remote co-author on a paper here, and at best probably some of the pedestrian tools that we use probably cite some of the work that was done here maybe a decade ago. So I'm not going to talk to you about anything from the perspective of the algorithms and techniques that I assume most of the conference will focus on, but I hope that I'll interest you, for some of you introduce you, and for others interest you in a type of data and type of data usage that your techniques can have tremendous play. They do. Again, we're probably using things that are a decade too old, and I think that as the field advances, and I'll say more about this, we're going to need much more and much better. So the title of the talk is Small Data, sort of N equals me. So I'll be going into this in more depth, but where the focus on big data in many, many fields is usually about big N, and the more N, the merrier, right? The more people, the more you can aggregate, the more you can bottle across, the better. And that is true and good. But there's another opportunity in this space that has to do when you actually just get to focus in on the individual and on the range of data that we as individuals generate, largely implicitly. And so that's in the broad what I mean. And I'll start off talking about this mostly in the context of health, where I've done the most work and where I think this is advancing the earliest and where the opportunities are pretty clear. But keep in mind that increasingly people who look at health really recognize that a lot of the health issues we face are as much about life and lifestyle as they are about particular medical conditions. And just more broadly, as I'm talking about things that sound more like the quantified self, which tends to be focused more on health and wellness issues, this could have just as much play when you think about the quantified student in the context of all the online and digitally based learning that's happening, quantified consumer, quantified commuter, and so forth. But let me ground it initially where it has been grounded to date. So if you think of this holy grail of personalized precision medicine, it has been advancing through extensive use of computation, and I believe that a lot of the work done here, and you'll even find papers referring to these different contexts, such as big data mining across electronic health records, the sort of work that Eric Horvitz and other people do in terms of mining web mining for being able to discover previous unknown side effects of a medication just off of discussions going on blogs. And that's a really still just begun to tap the power of that, in part because we've just begun in this country to more systematically move towards getting digital health records to happen and have data liquidity and all of that. But very important, great stuff, has contributed and will continue. That second sort of pillar of this approach is in all the omics, right? From genomics to metabolomics, it can't be done without huge computational support. The volumes of data are tremendous. What you can do based on reasoning from a model of understanding the mechanism is very poor, because you really, in that space, there's so little really understood about what's going on in the context of genomics. It all has to be discovered through analysis. Also, very important pillar to this. And what I want to talk about, though, is this, if you will, a third pillar. It has to be the same height, otherwise it's not a pillar. I'm not going to argue about the relative girths of these things, but at least another component here is on these data about the particular individual whose health is being managed. And so mobile health, the digital traces we generate more broadly, and how we can harness these things that were previously unmeasured about an individual's function and behavior to fuel personalized medicine. So to ground this even more, let's just take an example. So a patient with rheumatoid arthritis, maybe mid-40s, early 50s, tends to strike at around that age, tends to be more in women. And the nature of rheumatoid arthritis is that it wanes and waxes. It's something that has flares. They don't understand the reason for the flares. The flares aren't particularly predictable. And currently, as you're trying to find a treatment that works for an individual to maintain her at her best function and to have the least pain interference and interference with her job and personal life, you're trying to balance basically an optimization problem between excessive use of medications that have their own both short-term and long-term side effects, steroids, primary course of treatment, and wanting to keep the pain interference low from the inherent symptoms of the condition. And also, if flares aren't treated and they're allowed to get worse, they become much more intense than if they're treated early. So, and there isn't enough understood about the mechanisms to be able to predict how much does this individual need. It's not like blood serum cholesterol. It's not like cholesterol, where they understand sort of pretty well, without that much variability, how much Lipitor you need to take to maintain healthy blood serum cholesterol. In context of rheumatoid arthritis and Crohn's and lupus and all of this sort of family of inflammatory autoimmune diseases, it's much more empirical than that. And so the individual is going back and forth with their clinician, if they have access to that ready access to good care, trying to find this optimization to minimize their number of flares, to minimize their intensity of them, to keep down the extent to which they have to use a medication. So why am I telling you this whole story? Well, right now, the feedback process in all this is an individual coming into the doctor's office after they've been put onto a new treatment plan, and there's a standardized instrument. But the instrument is a set of questions that you get asked about how has your pain level been over the last 2 months or 6 weeks or 6 months since your treatment plan was adjusted. And that level of retrospective recall, particularly with respect to things that have their own natural variation and confounding factors, is very difficult to do accurately. We have a feedback loop with really poor integrity, veracity of the information that's coming back. So there's a lot of work going on to try to understand the disease better, the science of it, and there's work going on in just how, in the context of what isn't known about it, do you help to treat such patients. But the current situation is that 80% of all RA patients have flares at unpredictable times. No one is symptom-free even under treatment. And this treatment has other side effects you're optimizing with. And these newer biological agents that are produced, sold, and used, if you look at the numbers, it's really shows you that not enough is known about it, and it's not enough just to say, let's use the best of the biologics, because it's only in 15% of the cases that they get 70% better. So whether it's rheumatoid arthritis or Crohn's or lupus, or in some cases behavioral interventions around obesity or depression, anxiety, chronic pain, all sorts of chronic diseases where there isn't yet a really good blood-based biomarker for you to fill in and get really good signal. What I'll be talking to you about is that this n equals me, this small data, can help to fuel these important feedback loops of health. The one I've been talking about more is to the clinician. How does the clinician know in a more with more temporal resolution and with more accuracy than what they get just through retrospective recall, how this patient is doing on this new course of treatment? The patient might be expecting a really dramatic improvement, And to them, nothing has changed. But these medications take a long time, and the extent of improvement is subtle in many cases. So you don't want to ignore the signal. This is actually a good course of treatment to continue with. And so that's a big piece of the feedback loop. There's also just the self-care piece of the feedback loop. So if you're on pain medication, it is given to you with a prescription that says take as needed. And then the individual is faced with their own optimization, perhaps with a family member, of how much of this pain medication to take. For the most part, these are addictive pain medications because they're actually developed for acute pain. And your body desensitizes to them, and so they naturally have this addictive quality to them. And there's a huge problem in this country, for sure, other places as well, of increasing overuse of opiate-based painkillers. And that whole question of how much do I take in order to function versus worried about becoming addictive, not to undertake, not to overconsume. How do I get a better look at what is optimal for me? And then finally, one of the reasons why we don't have more personalized precision medicine is not really affordable. The amount of interaction you need with a clinician now to maintain and really get that level of information about how you're doing is too labor intensive. And there's really no evidence for it. So in healthcare, we have this problem, which is that you can't do, a doctor is not supposed to be creative, right? It's an odd thing to be in working with health professionals because you are not supposed to be creative. You're not supposed to reason about and, hey, this sounds like a good idea. Everything has to be evidence-based, which makes sense when you realize how little is actually known about the mechanism that you're treating. So you can't afford to be creative. You can't reason from first principles because you don't have enough of the information about those first principles. So things in practice can't happen until there's evidence. And there really hasn't been a scalable, affordable way of getting evidence about how people treat themselves and behave outside of a clinical setting. So if you ask a dermatologist whether diet influences your child's teenage acne, okay, whether there's something you can adjust in diet instead of putting them on Accutane, they will tell you correctly that there is no evidence for that. No evidence for that doesn't mean no, it just means there's no evidence for that. If you ask them what's the time, if there was going to be connection, what's the time constant? What delay should I look at? Is it an hour? Is it 12 hours? Is it a day? Don't know, because who would necessarily bother doing that kind of a detailed research study? And because in many contexts they're not. And I was just joking earlier, I've recently moved to New York City from really a lifetime, aside from graduate school, in California. And perhaps from the rate of my speech, you've determined I have been asked my whole life if I'm from New York. Okay, so I'm finally from New York. And as I moved to New York, I have found my inner Californian, which comes to things around healthcare. So if you ask a doctor in New York City from my limited sample about something that has to do with, well, you're having sinus issues, instead of taking some steroid-based nasal spray, should I try eliminating dairy? They look at you like, with this roll of the eyes and like you're from La La Land. And there is not any real evidence about these sets of things, including all the supplements that at least some of us buy in Whole Foods or other places, completely irrationally, perhaps with knowledge of that it's irrational. But we have no real basis of understanding what works and what doesn't, at what dose, over what course of time. I won't ask this because it's asking you to disclose private information, but there's some number of people in this room that take ginkgo biloba or glucosamine or these sorts of things you've read about on the web that you go to Whole Foods and you take with various consistency. I don't expect you know how long it takes for any of those things to take effect, for you to even know whether it would take effect. So the opportunity here is not just about how we care for ourselves, giving feedback to the clinicians, but there's actually an opportunity now to begin to learn some of these things that weren't affordable to learn, and it's in nobody's particular financial interest to do these studies without it being really inexpensive to do. So there's this opportunity to change where evidence comes from. Medical evidence largely comes from randomized controlled trials, and it will continue, and those remain important. Probably some of the biggest shifts about how these will be done is that you'll need less of a control group. You can just take your control group, from the web, from the ether, find that set of people. Increasingly, as we have electronic health records and stuff on the web, you'll be able to find your control group in the web to compare things to. But a randomized control trial, you take a medication, you do that randomized treatment randomize them to the two treatments. You find that one outcome, the purple treatment, gives 75% better results in 75% of the people. 25% did better or just as well on the pale blue one. And as my co-founder of OpenM Health, who is a real doctor, that means an MD, likes to say, when some Mr. Jones comes and sits in front of her in her office, she doesn't know if he falls into the 75 or the 25%. Now, if it's chemo or surgery and all sorts of really not reversible treatments, that's all the information she gets, and she just has to work with it. But if somebody has a chronic condition, then they're going to be on this medication for a long time. They're going to be on it until a better medication comes along, because chronic conditions don't really go away. One of the reasons that health payers in particular are starting to introduce really serious programs about preventing diabetes is because, for the most part, once you go from being pre-diabetic to diabetic, it's very hard to turn that physiology around. And once you have diabetes, you largely have it for life, and then you're managing it for life. So if she's about to put somebody on a course of treatment, the opportunity now to find out what works better for that individual. Put them on one, have a washout period, put them on the other, do a bunch of this passive measurement that I'm going to be talking about, and determine what's better for Mr. Jones. And in doing that, be able to contribute to the evidence base that might eventually lead to a better understanding and predictive understanding of what differentiates that 75 from that 25%. So in that same example of rheumatoid arthritis that I gave before, it does have to do with the opportunity to use this in the course of treatment, but it also has to do with being able to just use these technologies to help move the evidence base and the science forward. So Bob Darnell, who runs the New York Genome Center, is looking at a cohort study, looking at people with rheumatoid arthritis and having them do blood spot samples once a week. So that you can actually do the RNA transcription analysis to try to see what's going on in the course of the disease as somebody's going into what they call a prodrome, before they go into a flare. Because currently, they only have blood from people when they're in a flare, or after they've gone into a flare as they're treating them with medication. And just the logistics of all of that, being able to have access to people through their mobile devices, with just the mechanics of reminding people, having them take a photo of the little barcode that they put on the blood spot, because now you suddenly have a timestamp associated with that blood spot, just this mechanics. But in addition, we're measuring passive activity of that individual, because what he really wants to do is, when he sees signs of that maybe their function is starting to decline, and he wants to get daily blood pricks from them. And if you're not a type 1 diabetic, it's very difficult to get 6 months worth of daily blood pricks. He wants to do adaptive sampling. And so data about how somebody's function can also feed into supporting this kind of science. So in the large, it's about leveraging this as a sweet spot, although, as I'll discuss, it's not just from the mobile, but now, for the most part, increasingly, everyone is walking around instrumented, and so it is both a continuous source of data about me as an individual, as a way of interacting with me as an individual, and it's about gathering those data and the algorithms to turn that into some sort of actionable data for an individual. One way to think about this goal in the context of health is that really, if probably most of the people in this room, or you or a loved one, is diagnosed with something, you will go see a specialist. And you will be treated through frequent interaction with that specialist to do that optimization. But most people in the world, in this country, for example, most people would be treated through interaction with a primary care physician. Rheumatoid arthritis, depression, anxiety, Crohn's disease, chronic pain. For the most part, you're just going to get to see a primary care physician. And in many contexts, and then certainly worldwide, people are treated in a clinic where you're being treated by primary care physicians, but by an array of them over time, and there's not some individual. And so part of the opportunity here is to bring some of that precision of treatment, that method, to primary care and clinic-based care, and really across a range of conditions, many of which I've mentioned. So let me go down a little bit into the type of data I'm actually talking about. I would expect most of you have used and worked with and seen these types of data before. So, hello? Doesn't want to advance for me anymore. Any clue? Sorry. Play, slideshow. Okay. Nope, doesn't like this slide. Okay, I'm gonna tell you this next slide, but I'm gonna manually skip over it. I don't know what its problem is. You see it this way? Now you see nothing. Okay, let me keep going. So one of these, tricked it. So one of the primary sources of data that we've been using most aggressively, and actually a lot of this work started long before we had smartphones, even in the days of PDAs. People started doing work with being able to capture GPS time series for looking at different patterns. And people have been using step counters and accelerometers, actigraphy data for quite a while. But now we all walk around with the ability to capture actigraphy. That's continuous measurement of your movement. So at the minimum, and what's often most relevant here, is just sedentary and versus ambulatory. But in other contexts, you also can get speed of walking and other things from it. So it's accelerometry. It's really geolocation data. Only sometimes does it come from GPS at this point. We use all kinds of other RF information to be able to get geolocation data with lower power consumption on the device. And the opportunity to have continuous 24/7 activity, location, time series about an individual is really very rich. If that's all we had, we could already do, and have been for a while, do a fair amount of this. Because think about that example of the rheumatoid arthritis patient. Instead of now coming in and saying, well, in general, I think I'm doing a little better, had a couple of harder days, but I think I'm doing better overall. Now it would be some representation of what time she leaves the house in the morning every day over the course of the 6 weeks or 2 months she was last seen, and how many hours she spends out of the house, and how long are her ambulatory periods. Those are not bad indicators. They actually correspond to some of the more specific clinical questions that somebody treating somebody with rheumatoid arthritis asks, because morning stiffness is one of the symptoms of the disease, so getting out of the house. Somebody's general level of pain interference and disease interference is often reflected in how much time they're out and how much they're actually physically moving around. Now, at this point, don't think throughout what I'm talking about, I'm not talking about doing anything diagnostic. I'm not talking about having a model of what an RA patient looks like and then being able to apply it to your pattern and say, you fit in here. Right now, and I think for some time, the biggest power of this is to say for an individual, relative to her baseline, how is she responding to treatment? Or is she going into a relapse? And to inform that optimization problem for the individual. Ultimately, we'll have lots of this data and we'll get the priors and the models and the predictive part of it much better. But there's tremendous richness and applicability in even pursuing this a patient at a time. And I think that's one of the great potentials here, is that we don't have to wait for mass penetration of the technique in order to benefit from it. Other data just comes from the mobile apps. The reason that people buy and carry these phones with them, that it is the last thing they stop paying for if they're in economic hard times. It's the one point of connection to the internet for people who don't have as much discretionary income or very little at all. And we use it because we can run so much of the logistics of our lives through it. And it's by using it, yes, it's with us, so the activity location is then something we implicitly generate. But the apps we use generate analytics, as you all here know. And there's information in that analytics. So there's information in when I play, the games I play. And there's information in how I do on them. So when you play words with friends and the words you use with friends, right? And the same for email and the work that's been done on things like Facebook postings and sentiment analysis on Twitter and Facebook, these more publicly available feeds. But the private communications we do, the opportunity to use analysis of how I use it to produce data analytics for me is what I'm talking about. Now, there are health apps themselves, specific apps that you can use to get information from people that are beyond the standard instruments, the questionnaire. Like the standard way of getting information on how somebody's feeling, their mood or their affect, which is an important indicator in many contexts, is to ask them the PQ9, a 9-point questionnaire about affect that's been measured and validated with however that means. I don't know what you validate it with because there isn't actually a physiological way of understanding mood, but it's been studied and it's been validated as much as you can. Here's an example of an app that J.P. Pollack, who did his PhD several years ago at Cornell Ithaca with Jerry Gay, developed and tested and showed to be as reliable as the standard instrument. Have any of you seen this? So it's called Photographic Affect Meter. And if in the context of a study or an app or whatever, an app usage response, you want to get somebody's information about their mood or affect, instead of asking them a 9-point question, this app pops up, and they simply tap on the image that reflects their mood. And the images are not the same all the time, so you don't always choose the banana, right? You don't get it. It's randomized, but he's taken photos off of available photo sites and did very systematic studies to show how it compared to people answering through a standard questionnaire. So some of these apps are just things we use anyway. The way we tweet, the way we use Google Maps, when and what we do when we're using games, our emails, our calendar, and our communication patterns. But some of them might be explicit apps like this. Another app I like to point to was put out by the Veterans Administration for returning soldiers who have PTSD. And it's an app that's a portable tool to help individuals deal with their heightened anxieties. So panic attacks, as we would think about them, as they come back to civilian life and are exposed to things that might remind them of their trauma, but actually don't represent a safety concern. So this app gives them a tool that's in their pocket in between their therapy sessions to help them do guided relaxation, breathing exercises, prolonged exposure exercises, things of that sort. And we've done work with the VA so that it's not just a portable tool for the veteran, but that the data about how they're using it and how they've used it in the week between therapy sessions begins to become data for their clinician as well. One of my favorite startups in this space is Ginger.io. And they're a startup out of MIT. They're now largely California-based. And Ginger.io is really doing this. They collect passive data, activity, location, and communication usage, and phone call. And they have their machine learning engine that takes this back and is doing analysis for an individual to compare them to some of their models that they've been doing, but also, as I said, compare that person to their baseline. And they are working with folks like Kaiser Permanente to use this as a tool, for example, to monitor type 2 diabetes patients. One of the biggest issue in type 2 diabetes is adherence to medication and to dietary regimen so that your diabetes doesn't become worse. If you don't adhere to when you're diabetic, there are severe physiological consequences. And they become more and more severe. And so helping a diabetic actually adhere is key. Again, it's one of these things, once you have kidney damage, you can't roll back from it. So what Ginger.io is doing is this data, with the opt-in by the patients themselves, is coming back to the clinical care system to help the clinical care system identify which of these type 2 diabetics might be becoming or exhibiting symptoms of depression, because they have found in studies depression works against adherence. Intuitively not surprising. And so they've had very good results in helping the clinical care system then focus in on those individuals that maybe need some more intervention earlier to help them with their adherence. And Ginger.io has a number of other health examples out there. Very interesting company. Just another example in this space is a colleague, Tanzim Chowdhury, and colleagues again from Ithaca, coincidentally, has a tool, whereas Ginger.io is a tool for the clinical care system. Mood Rhythm, where am I? Okay, Mood Rhythm is a tool for bipolar patients themselves. One of the very important things in managing bipolar is to try to maintain good diurnal consistent rhythms, sleep patterns, work patterns. This has been associated with helping to better manage both the episodes, the frequency, and the intensity. And so it's a tool that through this passive monitoring, instead of requiring everything to be carefully journaled by the individual, helps that individual see and guides them towards maintaining better rhythm. So I've been talking about data streams that are largely just implicit, passive, and software-based, and just leveraging this main device. And but of course, there are real sensor streams too, right? Those physiological things that can be measured by an increasing set of wearable medical devices and wearable consumer devices. And I don't mean to say that these are unimportant, but I don't think that they're more important. If you look at how analytics has changed businesses and the world and how we do a ton of things, it's all and so much through secondary use of digital traces that are left behind through use of software-based services. And there is that same value back for the individual that's possible, even without, but certainly we don't have to say one or the other, in conjunction with these particular physiological things when you can measure them. But you don't have a device that measures what's the state of your rheumatoid arthritis. There is no device that measures what's the state of your Crohn's disease. There is no device that measures what's the state of your pain. And so while these devices are important, in some ways they sometimes, I think, take away from looking at the intelligence an individual can get from all the other data streams they generate. And to take that further, it's really much more than just about mobile. So it's way beyond mobile, and as I said before, it's way beyond health. So there's our household cable boxes. It's another source of data about household rhythms. When I'm working with some folks at Time Warner Cable, and one of the VPs there who's been very supportive of starting a small testbed in New York City to explore this small data concept, her example, which is a little not as easy to achieve as it sounds, she said, I get it. I'll be able to convince my father-in-law that his hearing really has declined over the past year. Because I can show him the extent to which he's been amping up the volume control, right, relative to 12 months ago. So no one big killer app, and really not any one data stream that tells the whole story. But we live our lives so digitally that when we think about how for an individual or for a household, we could bring these data streams back, data from the mobile carrier. A lot of what we do, we capture much too much information, and then feature extraction, we throw most of it away. A lot of that location time series for that rheumatoid arthritis patient, and certainly for older patients that tend to have less smartphones at this time, you can get that information back from data that the carrier has or could have. I think one of the most interesting data streams that we will increasingly be able to leverage is our financial transactions, all those swipes we do during the course of the day. And the opportunity, maybe for the first time, to have an estimate, actual measurement around dietary consumption, whether you're trying to look at gluten consumption or dairy consumption, and did it really make a difference this winter season that you had, reduced extent of your colds and congestion because you actually eliminated how much dairy you and your family were consuming. That's not something you see overnight. And it's a little bit of a hard thing to just keep track of. And yes, you can take pictures of food, but that's of limited duration and generality of use. Social, all the data that we can get from our social and communication patterns. There's a story I tell in my TED-Med talk, which in part started me thinking about all this in retrospect, which was from a couple of years ago. And my father, who was in the field of computer science, but was 90 when all of this began to occur, and he passed away a couple of years ago. And in those months of his decline, which wasn't preventable, it was his time. I'm not trying to tell you a story about if only we'd known what we could have done. In this case, we just had no clue what was going on. And he went from being this incredibly functional 90-year-old caretaker of my mother who's not well to somebody who couldn't function almost sort of overnight, and we had no clue what was going on. And his cardiologist had no clue what was going on. Didn't show up in his EKG. And when I took him to the emergency room, the attending there looked at me like I was some, neurotic daughter who wasn't willing to accept that her father was 90. But because the 90-year-old man presented to him as a normal 90-year-old man. But that 90-year-old man was entirely different in the way he was behaving than 2 weeks ago. And none of this shows up in the electronic health record. But when I started thinking back, I realized that, wait a minute, he'd stopped responding to email. Now you might say, Deborah, why are you expecting a 9-year-old man to be responding to email? But he was among the first people writing emails. Okay, I was on the ARPANET from the age of 17 in 1977 when I went to Berkeley, communicating with my parents through email instead of having to talk to them on the phone. Much easier way to communicate with parents when you're 17 and go away to college, right? He was using email forever. He was always responding to our emails, and his email suddenly stopped. It also turned out, but we didn't know it, that his walks around the neighborhood became shorter and shorter and more intermittent, and he was an avid walker. And we only found out after the fact he'd stopped cooking dinner at home. Generally, he would cook a meal at home. But his purchases at the supermarket became lesser and lesser. He wasn't even aware of it. He didn't mention it to his doctor. He didn't particularly mention it to us. And we had no idea what was going on. And how would this have helped? Because his care team and the family and he could have had some knowledge of what was happening, could have had some way of letting him and us deal with that end of life in a somewhat different way. And I don't mean to be melodramatic in the way that TED Talks try to get everyone to be melodramatic. I'm somewhat self-conscious of the fact, but really it was part of what brought together to me how we could use these kinds of passive traces to help people, not with one killer app, not with always about saving lives, but helping us with times and contexts where we really could use better information. And so lots of opportunities here, from really being able to take our consumer transactions as small data and turn them into something relevant, like are we seeing a reduction or a shift in how much fast or processed food is being consumed? If you want to take an initiative in your community and try to encourage in the schools to have everyone start doing a competition to actually cook at home once a week and with more fresh components instead of processed ones, how do you execute on that? Well, our small data can start to feed into things like that. Communication as language patterns, not just the timing of that somebody has stopped communicating an email, but the language we use in our email. Looking at the range of vocabulary and sentence structure is indication of cognitive decline, of cognitive fatigue. A lot of the complaints around chronic disease and even some of the medications for them is people just complain about chronic fatigue, about cognitive fatigue. How do you begin to measure these things, let alone things like chronic fatigue and other disease context in which we're working? And in all these cases, it's no one data stream. As you guys all know, you get data from different sources, sensor fusion in that sense, and it's about integration and fusion, and it's all about the sense-making. And it's sense-making across these noisy time series. And you want to be able to do correlation. Eventually, you want to be able to understand things around causality. But initially, it's really how do we model the individual by being able to run algorithms across their time series to look for their responses, to feed back into their care, to feed back into what we understand, as I was saying before. So that's why I started doing this work in the context of Open Health. My early background is internet protocol stuff, and I grew up with the IETF and other structures in which you have open modular infrastructure, and that's how you get amazing commercial ecosystems. Sometimes when you work with people in health, I found myself for a while talking to people at NIH and Washington, D.C., and as a joke, I started saying, open source is not socialism. And the first time I said it, and I was just being flip, I realized by the look on the person's face that I was actually telling them something. And so this whole, in the context of health IT, and part of the reason why we have such horrendous health IT in this country is that it has not emerged with any architecture or modularity or openness in that commercial ecosystem. And eventually this will be tying this back into those electronic health record systems, getting data from them, figuring out what data from these small data streams actually are clinically relevant. So let me end by mentioning sort of the two key challenges here to make this come true. One is, and the main one, is how do you make clinical sense out of raw data? Or application sense if you're applying it in the context of something like quantified student. So folks I've talked to in education, when I show them that picture of the N=me data serving the patient, the clinician, and creating evidence, they say that's the same story we have in education. How do we help that individual student optimize the practices and the studying and the modalities to fit to their learning? How do we optimize what the teacher and the teaching system knows? And can we take advantage of the fact that they're acting out their learning digitally? How can we start to learn more about how people progress? But we have the raw data, that isn't the problem. Actually turning it into something meaningful, all the modeling and analysis that you guys do is what's critical. And I tend to think about these things as, if you will, sort of behavioral biomarkers. We don't have blood-based biomarkers, but through a layered architecture, can we do easy to do the lower level state classification, starting to do that summarization, and then for a particular condition, you're looking at different actual metrics that are relevant. So 80-90% of this is the same of the underlying machinery of what you need for chronic fatigue or lupus or RA or Crohn's or depression. But when you get down to that individual condition, there's gonna be some different trend and marker that you're gonna look for that's specialized to them. And so we need modular tools to begin to do this kind of identification, complicated slide, but it's just something you see in work that's been done for years in the context of whether it's audio data, voice recognition, image recognition, and the community is starting to have more of a modular shared approach to this so we can all get better faster. And the second challenge that I want to end with is really about governance. So our mobiles happen to emerge thanks to the iPhone and Android, in which the control over what you run here and data you collect shifted from the carrier. It used to be that AT&T, Verizon, et cetera, determined what software ran on your phone. And now, because of app stores, we decide what runs on our phone. We register for accounts for Runkeeper or Fitbit or, iTriage or PTSD Coach. And so we actually have personal access to the data that we generate through these by and large. But that is not as true with respect to all the online things we do or the financial things we do. While you can get access to your data, in many cases and increasingly, I think Google just announced yesterday the ways in which you can get access. You'll be able to do an export of your calendar and Gmail data. There aren't standardized open APIs, personal data APIs. Whereas a user subscriber, I can opt in to programmatically get my data to come back to some sort of a personal server in the cloud where I can then run apps and services over them. And I believe that's the model we need. So I'm not saying that everyone is a quantified selfer, okay? That's on the East Coast again, I have to explain. Quantified selfer are those narcissistic Californians that like to measure everything about themselves, right? And then they do their Python and R analysis and they go to meetups and all those things. Okay. But that's not how it's going to play out in large, right? The everyday consumer downloads apps. The everyday consumer, right, a decade ago, an app was Microsoft Word. And no consumer on the street felt that they had any connection to causing an app that was just specialized for them and their needs to come about. Now you hear people for years, you people talking about the app that they want to design, that they want to use. So think about the consumer downloading apps that's going to help them to optimize their commute, their consumption, their new intervention to try to help their diagnosed as ADHD kid. Does it make a difference if they change what they give them for breakfast and at mealtime? Yes. So, but to make this happen, the data is already being captured. It's not about introducing new privacy violations, because I'm not talking about any new data. I'm talking about just letting an individual get access to their data back via a programmatic way, and having standard ways that we begin to design apps that access those, just like you download apps that access your location, calendar, and so forth. And to the extent it has to do with privacy or those things, a word which just has so much baggage to it that I don't really want to use it, it does introduce transparency. If you are using the data that is known about you, there's just about being an educated consumer. You can, en masse, you can live in the world with having greater understanding and not be so surprised by this NSA stuff. So, as I said, it's not about health, it's really beyond that, about life. And we are doing a small data test bed in New York City and look forward to collaborations in other places where we can get a density of this kind of behavior. And then just to end with a really bad pun I said the other day in a meeting, this really isn't rocket science, but maybe it's pocket science.
So we have time for some questions. If questions could approach one of our program chairs who has a microphone. So Terry, if you want to perhaps start. And in the meantime, with the speaker for the next session, perhaps.
So fascinating talk. Actually, something you said at the end made me think it is possible to get your FBI records if you ask for them. I wonder if we can get our NSA records if we ask for them. And that might be a source of personal data that would be very valuable for us.
Agreed. Go to the aggregator.
One more question from Joshua.
So I have a suggestion. Maybe you've thought about it before, but with your phone, there's something you could do to get some of the randomization that you normally do in medical studies in order to infer causality between decisions that people make and outcomes.
Yes, exactly. And so I'm not on anymore. Oh, sorry, this guy. Ida Sim, who I mentioned, MD and PhD in bioinformatics from UCSF, and Rich Kravitz from UC Davis. We do some work together on exactly on that. And so there's a NIH project called Trial List, which lets you begin to do that randomization in the treatments that people, what they take and when, and the potential is all there, and that's starting to happen. I think it's a very important component of it.
Okay, we have time for one more question.
Thank you for the talk. It was really fascinating. I wonder if you can comment about, there was a study published in PLOS about a year ago. They surveyed a lot of papers that tried to use all sorts of mobile intervention and stuff like that, and found only 2 out of 80 had significant outcomes. And also we know that about the average time between the time people buy a Fitbit until they stop using it is less than a month. Yeah. So what is missing?
Right. By the way, did I mention Fitbit? Okay. Sorry. I had a picture of it. Okay. I have this little thing I'm doing. I'm trying to see how many days I can go without having a conversation that includes Fitbit. Nothing against Fitbit, but it's just been such a focus. So Fitbit already delivered, I think, they made progress in that they understood that they wanted to represent data back to the individual in some interesting way. The problem is that data is like on a web page and not as much in play. Whereas if you just go back to the great work that James Landay and Sunny Salvo did at University of Washington and the Intel Lab on UbiFit, the work they did back in the PDA days, I'm just curious, how many of you have read this? Seen UbiFit? So as you exercised, it grew a garden in the ambient display of your PDA. And then at the end of the week, it went clean, left behind some butterflies if you'd met your goal, and then you'd grow the garden again. And aside from this reaction, which is like, I don't want flowers growing on my phone, okay, so think about it as a fish aquarium or something like that. But the way in which you tie what you do to more ambient displays and doing this in a more modern way, what's been tested so far are like individual measurements and without the multiple data streams and without the interaction with the individual. At the same time, anything that is about obesity that addresses only activity, I think, is doomed to fail. We have to address the dietary component of it, and we have no way of measuring dietary intake. And anyway, most people don't have a whole hell of a lot of choice. Processed food is cheap and addictive. And so there are systemic problems on the side of this issue around obesity and our food environment that no Fitbit and different combinations of those data streams alone are going to address, which is part of the reason why I work more in the context of some of these chronic diseases and still trying to figure out how we're going to solve some of these more fundamental prevention problems that are much more market economics and food environment than they are any kind of self-monitoring.
Okay, if we can just thank Deborah another time for a very inspiring talk. Okay, so the next talk is Scalable Influence Estimation in Continuous-Time Diffusion Networks. This is a winner of an outstanding paper award. So if all the authors could come up quickly, I have money in envelopes so that I can hand those out. And if in the meantime, the speaker, Nandu, could set up. So we have any other authors? Just two of the authors here? Should be another one. Manuel. So, Nandu. Manuel Gomez Rodriguez. Hong Yuza. Lei Song. Okay, someone's taking the money for Hong Yu. Good.
Hello? Okay, sure, cool. Okay.
This is a reminder for speakers. They're supposed to come before the session and check this. So 10 minutes before your session for speaking to make sure you come and check your projector works. Okay, Nandu with Scalable Influence Estimation in Continuous-Time Diffusion Networks.
Okay, I'm very glad to present our joint work about the Scalable Influence Estimation in Continuous-Time Diffusion Networks. So now we are surrounded by social and information networks over which diffusions of information, events, variables take place constantly in people's daily life. So intuitively, when some influential users have been adopting certain new product, they will actively influence the behaviors of their friends, and which will further invoke a larger number of follow-ups for adopting this new product through word of mouth. So one particular question we seek to answer is, how can we predict how many users will be influenced by such influential users? And then, how can we identify such influential users to trigger the largest follow-ups in the future? So both the influence estimation and the maximization problem are interesting because advertisers want efficient and effective campaign for their new product. But they are also very challenging in that they are actually sensitive to time. So clearly, think about 1,000 buyers per day can be much better than, say, 1,000 buyers per year, right? And we want our solution to be scalable to deal with large real-world networks in practice. So in my following slides, I will first introduce our proposed continuous-time diffusion model, which can realistically approximate the underlying true but unknown diffusion mechanism. And then I will present an efficient algorithm for both the influence estimation and the maximization problem. And in the end, we are going to evaluate the performance of our algorithm by using both synthetic and real diffusion data. So traditionally, the diffusion process has been modeled as discrete rounds. A node can be infected round by round. But in reality, we know that the propagation can actually not diffused in rounds, right? But to model the timing requirement, people have to partition artificially the continuous real-time line into discrete rounds. But to be honest, it is really not trivial to decide how long each round should be and how many rounds do we really need. So to better model the diffusion timing information, we propose alternatively the continuous time diffusion model, where we explicitly model the mutually independent transmission time associated with each edge. So specifically, for each edge from node J to I, we associate a transmission probability density function over the transmission time, which is also called the transmission function, to describe how likely that node I will be infected at time Ti given node, sorry, because I cannot see the slide on my computer. Given node J has already been infected at time Tj. So from this new perspective, we can see that we actually have a network with random edges. And if we fix a particular set of sampled transmission times over the edges, the actual infection time for a specific node simply equals to the shortest path from the source. And then the inference value of a given set of source nodes can naturally be defined as the expected number of infected nodes before time t, which further equals to the summation of individual infection probability that a particular node I can be infected before time t. And to further calculate that infection probability, we can simply marginalize the joint likelihood over all the observed infection times. But you can see using graphical model inference. But as you can see, this integration is actually challenging in that we have to consider all possible infection state for each node before time t. And if we assume a general transmission function over the edges, we normally have no closed form solution. So to overcome the difficulties of the inference problem, we further transmit our original problem into a graph theory problem, where we do not want to calculate the infection probability individually, but rather when we have a given particular set of transmission times over the edges, we actually only care about the whole sum of this indicator function, which further equals to the size of the neighborhood given a particular source node, where the neighborhood includes all the possible nodes that can be reached within distance t. And then from these new observations, we can simply first draw many sets of independent transmission times over the edges, and then we can approximate that expectation by taking the average across all different samples. And to calculate the single summation here over a particular sampled network, it is really trivial to check whether or not for a particular node I, whether or not the length of the shortest path on this particular sample network is less or equal to my distance t. Thank you. And then, but we can see that only using this simple shortest path algorithm cannot be scalable, because to estimate the influence of a single source node, we have to run the algorithm one time. And then to decide which node is our best source node, we have to run the algorithm for all the nodes, which immediately will result in the quadratic time complexity with respect to the number of nodes. And this cannot be scalable when dealing with large real networks. So instead of calculating this individual shortest path for each node, we want directly estimate the neighborhood size by using Cohen's algorithm developed from the field of theoretical computer science. The basic idea is that given a particular set of sampled transmission times over the edges, we further drove M-independent random labels associated with each single node according to a unit rate exponential distribution. And then, surprisingly, by using Cohen's algorithm, if we treat each single node as a possible source, this algorithm can simultaneously estimate or find all the smallest random label within distance t for all these possible single source nodes altogether. And then we can simply estimate the neighborhood size using a very simple unbiased estimator based on the extracted minimum label using the property of exponential distribution. And if we have multiple sources, we can see that the union neighborhood of each single source has a property that the minimum label of this union neighborhood actually equals to the minimum label extracted from each single source. And then we just treat the minimum of all the list labels from each single source as the list label for this multiple source set, and use that to estimate the possible neighborhood size for this multiple source node. And so the overall algorithm actually includes two layers of randomization. First, we can draw many sets of independent transmission times over the edges, and based on a particular set of transmission times over the edges, we further draw M-independent random labels associated with each node. And we run Cohen's algorithm to find the minimum label within distance t associated with each source node altogether. And and then we can simply estimate the true inference function by taking the average across all these two sets of independent samples. And we can prove that if we drove large enough number of sets of independent transmission times, based on each of which we drove m sets of independent random labels, with high probability, our algorithm can produce a prediction with the error at most epsilon. This further implies that when we have a much longer time window, the estimation problem will become a little bit difficult because we need to draw more samples. However, in practice, we have discovered that if we have large number of sets of independent transmission times, this will actually enable us to use very few random labels to still achieve very good performance. So then, once we have this efficient influence estimation algorithm, we can directly plug it to solve the influence maximization problem, which is a bit hard in general. But the good thing is that our objective function is a non-negative monotonic submodular function, and the greedy algorithm can achieve at least 33% of the optimum value using the exact inference function. And also because the estimated inference value given by our algorithm usually introduces some estimation error, but we can still show that even with this small estimation error, the greedy algorithm can still have a performance guarantee only with respect to a small additive errors here. And so for the experiments, we use both synthetic and real diffusion data to evaluate our algorithm in terms of the accuracy of the selected, the accuracy of the estimated influence, the solution quality of the selected sources, as well as the scalability. So first, on the synthetic data side, where we know the true continuous time diffusion model, we compare our estimated influence denoted by the blue dot with the exact influence given by the exact influence algorithm. And we can see that across different networks of different structures, the estimated influence is pretty close to the exact value. And the performance is independent of the network structure. And when applied to the influence maximization problem, we see that on different networks of different structures, our algorithm can always at least outperforms the other competitors by at least 20%. And the performance is also independent of the network structure. And then to evaluate the scalability, figure A and B shows that the proposed algorithm is actually much faster in several magnitude when compared with the simple simulation algorithm and the exact influence algorithm. And the figure C verifies the case that if we increase the number of nodes to millions of nodes, the algorithm is still able to scale up. And finally, for the real data set, we first learned the continuous time diffusion model using 80% of all the cascades, based on which we selected the number of sources that can maximize the future influence. And then we verify whether this is true in the testing case by using 20% for testing. And in figure A, it shows that the estimated influence produced by our algorithm is closest to the true influence extracted from the testing data. And figure B and C further verifies our intuition that the selected sources can indeed trigger the largest true follow-ups within very short time period on the testing data. Right. And so to sum up, we propose a very efficient randomized algorithm that is able to scale up to millions of nodes on real network size, and with improved performance in terms of the accuracy of the estimated influence and the solution quality of the selected sources in real data. And for the future work, we would like to apply our influence estimation algorithm to other interesting questions, such as the social welfare maximization problem, the user engagement maximization problem, and to develop more general continuous time diffusion model. Yeah, and welcome to our poster in this evening, and the code will be released quite soon, maybe recently. Okay, thanks.
Okay.